Hey, what's going on, folks? It's Mike here, and welcome to our next module. I'm going to go ahead and dive into computer graphics here, and we are working on Module 4, and we're going to be continuing talking about rasterization as well as mathematics with this talk here. So with that said, let's go ahead and begin the module. As always, make sure that you do the in-class activity at the end. And here's a few useful resources for today's module. If you'd like, go ahead and peruse or maybe read through one of these. Again, you don't have to do all of them, but just reading through one of them I think will help. One in particular that I think will also be useful, not to inundate you with too many videos, is this Essence of Linear Algebra series by 3 Blue, 1 Brown, which is a really, really nice series. In fact, this is the way that, for me years ago, I really was able to visualize some of the mathematics that we used in this course, meaning the linear algebra. In fact, you'll see me borrow a couple of the actual figures from these videos because I think they're just so well done and so well explained, and it's always nice to be able to visualize some of the mathematics. So anyway, with that said, let's go ahead and jump into the slides here and go ahead and get started. So as mentioned here, during the warm-up, this is the really nice series from 3 Blue, 1 Brown here. And in this particular example, they're showing, and I'll illustrate this again, just sort of the transformations that happen when you, say, add two vectors together, which is something that we talked about last time. So again, you can just kind of see how this works here. So I think this is, again, really nicely done. So please feel free to support that series and learn algebra in that way. But with that said, I want to go ahead and highlight another pioneer of computer graphics. Today, we are highlighting Dr. Rebecca Perry. She has had quite a career, now is at, or was previously at Harvard, where she completed her PhD, but now works on, or had previously been working on, different sort of programs for previewing furniture. So again, if you've ever been to IKEA, Wafer, likely you've been influenced by Rebecca Perry's work here. Dr. Perry has done some cool stuff here. I'll go ahead and just click on the link here so you can see the sort of 3D models and visualization and some of the sort of mixed reality stuff that she's worked on. So here's the article here, and I thought that might be of interest for some folks to check out Dr. Perry's work. All right, so of course we're recording, so just some logistics about what is going on here. Assignment 2 is out, so again, keep continuing to work on that. If you have questions, stop by office hours, post on Piazza, etc., etc. And Lab 4 is also going to be out, and I'll show you a little bit of a preview of that. That'll be pushed to your repos by the time you're watching this video. Assignment 3 is also going to be for our next module, and we're going to start actually working in OpenGL. I'm hoping to do some more supplementary YouTube type videos for OpenGL as well once we get started with that, so hang tight for that. But for those of you, if you do happen to be ahead in this class for whatever reason, one of the parts of assignment 3 that's not related to programming, but I'm going to ask everybody to do, is to do a little bit of 3D modeling. So I've got a few tutorials here. Maybe I'll add one more at some point here. But to help you learn some 3D modeling, I try to add about one. You can watch any one of these videos and be in a good place, I suppose. But I think that'll be quite fun, whether you've done any modeling at all. But again, if you just want to get ahead or do a little peek at assignment 3 once you finish assignment 2, your goal is to create a 3D model in Blender 3D, or you're welcome to use any other 3D software if you like, Maya, 3ds Max, ZBrush, etc., etc. All right, so with that said, last lecture we were working on some linear algebra, primarily focused on vectors and coordinate systems. So we got a little bit of a review of that and some important properties that we will pay attention to, learn about some other things like matrices and so on. And again, your tools, or these things that we're learning, dot product and cross product. So again, dot product answering sort of how similar are two vectors, and cross product giving you a vector perpendicular to two other vectors, as well as can be useful for computing areas and some of these things too. But that was the primary focus here. All right. So just a couple things there. Make sure that you're comfortable with. And again, these visualizations coming from that nice Essence of Linear Algebra series by 3 Blue, 1 Brown that I referred to. So feel free to check those out. All right, so today again, we're going to continue talking about rasterization, sort of round 3. Again, you know, in a nice sort of analogy to think about rasterization is from this image here, where you're sort of filling in pixels, or thinking about rasterization as filling in pixels or tiny fragments here, you know, one at a time to approximate this image here. And that's what creates the actual final image. Okay, so you can kind of think about it like looking through a screen door or a screen window and just filling in those pixels. Okay, so that's what you're working on for some of your previous labs, for instance, getting that to work here. All right, so where we're at so far on our great looking render here, or render, you know, we've been working on this software render, and we're, you know, starting to get to some things, some interesting things here, like actually getting some transformations. So you're working on at least filling in those transformations and then thinking about multiplying some matrix transformations. I think today you'll have a little bit more intuition as to how those work, but you know, you'll have some sort of spinning triangle here shortly. Okay. So I want to talk a little bit more about how we're going to render 3D shapes, again, just to gain some intuition on these transformations. So that's going to require us to revisit our fixed rendering pipeline. Again, that is the journey of a pixel or some geometry data all the way through the rasterization process, processing things as triangles. Okay. So here we are. Let me hop out of here. In our graphics pipeline. And, you know, we're actually going to take a look more at this transformation step here. So let me actually just highlight this again. I'll circle around here. Eventually we'll get into the lighting portion too, but we're going to focus on the transform part. But a way I like to think about this, you know, is really a vertex's journey, in a sense, from 3D to 2D, right? We have this sort of or I guess 2D to 3D, however you want to specify. But usually, you know, we're specifying our points with an X, Y, and a Z. And by points, I mean vertices. And then we're translating those or transforming them, you know, some set of transformations, get this on our monitor. That's our 2D computer screen in an X and a Y position. Okay, so we got to apply a series of functions, if we're thinking about this in math, to produce a point at some new location. Okay. So with that in mind, again, the steps that we haven't covered, you know, this transform portion here, this is the important part that I want to talk about today, okay? And remember, I showed this picture earlier, and I kind of skipped over it and said we would talk about it, but now is the time for us to talk about this. So let's go ahead and take a look at some of these stages. Again, not all these things are going to make sense here, but I do want to get some of these terms in your head here, just hearing them, so they'll again make sense as we sort of work through things. So you know, just kind of walking through the first thing that we've been doing when we've created a triangle, right? And you can go back to your Bresenhan's lab where we were sort of filling in triangles, right? We were just specifying 3 points. And how we say that is those are sort of the local coordinates. Okay, so we just sort of imagine each of those triangles that you created as having, you know, being in its own coordinate system, and they're just sort of plotted in the 3D world, being sort of just displaced from the origin here. So like this cube, for instance. Okay, it's just a cube in the center of the world, and that's really it here. Okay. So, you know, here's an example of those vertices that would make up the cube. You know, if you can imagine plotting these in 3D here. You know, this is easy, right? This is how, for those of you who have some 3D modeling experience, you create a 3D model, right? You just sort of create a new file and sort of start plotting the vertices out. So similar thing we've been doing. And it's just easy to think about it this way. Okay, here's a bunch of vertices, and, you know, where do we place them around the origin? Okay. But the next step, which is sort of the one that you're going to hear, is sort of this idea of moving those coordinates into what we call world space. So if you read this box, I know the font might be a little bit small, but it says local to world transform. So this basically means we're going to take this cube and move it somewhere in the world, okay? Because we don't want it to be at the, in its own location, but we want to actually place this somewhere on planet Earth, right? So it's got to walk somewhere or translate somewhere, etc. So, okay, what does that mean? Well, basically what we're going to do is move things into world space. So again, that just means transforming this cube somewhere in our greater world. And we have something called a model matrix. That's just the name of this. You could call it the world matrix or world space, and people know what you're talking about. But usually a model matrix is what we have, and that's how we, or where we store our transformations for some object here. So this cube, if I want to transform it and move it to the right on the x-axis, 2 units, whatever that is, 2 meters, whatever, that's what's stored in the model matrix. And I multiply that model matrix by this cube's local coordinates, and then it's in the world space, okay? And of course, we can move things, scale things, rotate them, and perform all sorts of other transformations if we like, okay? Now, there's some optional steps that I've skipped here, like object removal, meaning like, hey, we just don't want to deal with this object. And then other things like backface removal, which would sort of mean like, hey, if I have a triangle, only, render the first side. I don't care about these as much, so we're just going to move down here, which is the next step, which is the view space, okay? That's what I've highlighted here, 2 different steps here. But you'll notice another transformation called world to camera transform, okay? And this basically means, okay, we've moved this object in the world somewhere, but now pretend you're a Hollywood film director. And I'll do this the best I can by popping up here, right? So you've translated yourself. So let's say we've moved backwards. I've gotten smaller. And then, I've moved in the world, but now the view space is, the Hollywood director with their camera is going to sort of place it somewhere. So maybe right in front of the subject, maybe, up high at an angle. And then that's the actual perspective that you have in your scene. So there's another matrix that's multiplied, and we're going to talk a lot about matrices here, that positions the camera for how you see in the world, okay? So I hope that makes sense. Pretend you're in a theater, like in a play. You yourself have your own local coordinate system. That's step 1. And then the stage director says, hey, Mike, move 2 steps to the right. That's this world transform. So you've just transformed, a model matrix got multiplied into you, and you transformed some direction. And then someone comes with a camera and actually films you, and then that's what the world actually sees, okay? So you have your local coordinates, then you transform to world space, and then into view space here. There's this other box here that says object space clipping. Well, if something gets clipped away, that essentially means you moved out of the scene. So like I'm doing here, right? I'm out of the view on the camera that's in front of me. So I'm essentially being clipped away. We just don't have to worry about me if that happens. Okay, and then the next step here is, which is also part of this view space transformation here, is this perspective transform. Okay, so what exactly does that mean? Well, there's different types of lenses you can have to see the world. Okay, we're going to talk about, or I'll call out 2 specific ones. I'll call them out at least twice, but the most common one is a perspective transform. But the way to think about this is, I've got my Android camera here, and I've got a lens here. But for any of those folks who have taken photographs or done photography, you know that I could also have a sort of wide lens that gets a panoramic, a very wide view, or a fisheye lens, which sort of distorts things a little bit, okay? So that's different transformations that can be applied after, different filters. Again, if you've played with like a Snapchat or an Instagram filter or something that sort of distorts the view, that's something that could happen here. All right, and then the next step, or here's sort of an example of perspective. What I mean when we talk about perspective is, if you've ever stood at the end of a railroad track, which, be careful, as you look down, it appears like the tracks are merging, right? You have this sort of foreshortening effect here, where everything's coming together. But that's perspective. Things that are further away sort of get smaller, but they also sort of converge at a point, okay? So with that idea in mind, this is a perspective transform. Things that are further away can converge, and that's how you convey distance, right? Something that's smaller, converges towards the, some point here. All right, now it's worth mentioning that there's some more optimizations we could do. Again, clipping away objects, things that don't show up. Geometry doesn't show up. Again, that was sort of part of this object removal step. But again, there's sort of this clipping step here. So that's clip space. Again, consider me a bunch of different objects. My hand here, if it's off the scene, we just don't render it. We don't rasterize it. We just don't have to worry about it, right? Because it was here and then it's not here. So you don't have to see or worry about it or waste computational power rendering that hand. All right, so finally, the next step, once we've projected our visible points on the scene, that's we have everything from the right perspective and so on, we go through this step here where we convert our vertices. So let me pop up here again, so that they have everything in sort of a graphic space again is normalized. So it's between 0.0 and 1.0. So maybe the top left corner of your screen is 0.0. Slide over here, that's 1.0. And sort of slide down here, this is 1.0, 1.0, whatever. So there's some sort of normalized system where that could actually be flipped, where 0.0 is the bottom left corner, top right corner is 1.1. But anyways, those sort of coordinates don't make sense for us. If I said, hey, plot a point at 0.96 comma 0.52, usually we're used to working with screen resolutions that are something like 1280 by 800. So we do this sort of transformation step here and get things in what we call screen coordinates, because usually, again, humans, we work better with sort of integer numbers in this space. So that's just a simple transformation done there. I guess it wouldn't have to be required, but it's something that makes our lives easier to reason about our graphics here. All right, and then step 10 here is, of course, what you did in your lab, rasterization, right? So we've actually got some triangles, they're projected in the right space, they're in the screen coordinates, and then now you just run, your triangle fill routine here, whatever it is, okay? So as you can see, this is quite a journey that a 2D point takes to become a 3D point. And all these terms here that I'm sort of talking about or going to use or mention today, they all repeat, in our OpenGL programming, or maybe you're going to go do Direct 3D or Metal or whatever. The same sort of like pipeline is what's behind the scene, okay? All right, so with that said, let's talk a little bit about some of these spatial transformations, because it's one thing to say, hey, there's, this sort of pipeline within a pipeline, but let's figure out what's actually going on here, okay? So what is a spatial transformation? Well, just some transformation that, if we're giving some input, we should get some new output, okay? And again, since we're working with geometry here, that means that we're getting a new position for our coordinates here. So you can see this cube here. This is a nice example. This is the Unity 3D game engine, but where I'm scaling, rotating, and translating some object here, okay? All right, now where are transformations used? Well, everywhere in computer graphics, as you can imagine. I don't need to spend too much time here, but you can see some rotating shapes here. So gears, moving a camera around, for animations, shadows and everything, right? So you sort of project a shadow, which we will do shadows later in this course. So this is kind of cool. So all these different things get used in this course, and in just computer graphics anyways. Now I want to provide some intuition on these transformations, though, because really all we're doing when we're applying transformations, it's important that you keep in mind that we're doing this to individual points here. So I'll draw your attention to the top right here of the screen here, where I have this vector that's pointing at a point here, and then I'm just moving it here, right? So that's just a transformation here of what's going on. Okay, and if you watch that 3 blue, 1 brown series, you'll get this intuition here that what we're really doing, again, is sort of shifting or manipulating a grid here. We're changing the coordinate system once we apply a transformation. Okay, that's sort of what the linear algebra thing is doing. So it might be useful to think about it like this, right? The point doesn't really move, we just move the system or the coordinates. Now that might not be a little bit, maybe that's not intuitive from watching these two animations here. But it is perhaps useful to just think about a few of these sentences I have here. Okay, so one here again, if I just go back here, let me go back a few slides, right, where I was talking about this diagram here. It is just useful for us sometimes to think about these transformations in different spaces. Again, that's a convenience for us. Is this thing in local coordinates, world space, view, screen, etc.? Because in theory, we can always plot the point at the right pixel. It'll just be a lot harder, right? And you can imagine when we do rotations and these types of things, it gets even more confusing. So for now, just know that each transformation or a series of transformations is going to move us into a new sort of space that's convenient for us to work on. And the reason this works, or why it works well, is these transformations are linear transformations. Okay, this is where linear algebra comes from, but the transformations are what we say linearly independent. That's important because one, it means we can do things sort of in parallel, and then they're also very simple computationally. Okay, and this matrix, which we talked about at the end of the last module, that's our tool here. Okay, that's going to encode this information of how to transform a point. Okay. So here's an example transformation. Again, we talked about moving around vectors. So I said this would show up again. But an example transformation, right, for adding two vectors together. I mean, first you could just think about it like a line, which they do in that video nicely. But here's the first transformation. Here's the other vector. Then we're going to transform this point, right? We're just sort of putting it at the tail and then following the head here. Okay, so a series of transformations, adding the x components, and that happens linearly independent, right? 2 plus 5 here. You can just do that on a number line here. Here's how we add things. But then you do that to other, transformation on the y components here. So the 2 here, and then the -1, right? We add these components together. Okay. So again, let me just go ahead and show these different transformations that we're going to be doing here on this little cheat sheet. And this is what we're really going to talk about today, just understanding how 3D transformations are encoded in each of these common operations that we do: rotations along different axes, scaling, and translation. Okay, and let me provide a little bit more intuition into these as well. Okay. So the first thing, you're looking at one of these. I just grabbed one. They're all 4x4 matrices. We'll talk about why in a moment. But so each column in our matrix describes a vector, right? So it's one, well, I guess depending on the system here. And let me make a little correction. It doesn't matter how I do this, but it's sort of one column by 4 rows. So rows, again, go across, columns go up and down here. And each of these columns describes where a new point will land after the transformation is applied here. Okay, so in an X rotation matrix, this first column here is what we're doing to the X coordinate. And we're essentially just multiplying something by 1 here, which means it's not going to change. And then we're, not doing any other operations here. Okay. And then the Y column, or the next column of the matrix, this is what we're going to do for where our Y coordinate, our new Y coordinate will land when we're rotating something about the X axis. And then similarly for the Z coordinate as well. And then the last column here is sort of an extra column, and we'll talk about why this is set up, but there's a 1, so it's not really shifting or moving anything here. But that's the idea here. Okay. So anyways, let's talk about some of these transformations, some of these common ones from our cheat sheet, starting with scaling. Okay. You can see an example of scaling here, making this object larger. And again, when you see this object move as a whole, it's a little bit misleading perhaps here, right? But I do want you to think about this as 8 individual points that are being scaled here. So there's a point here that's moving, another point in the corner that's moving, another point here, another point here. It just happens to be, since they're connected, that it looks like a cube that's stretching out, but it really is just 8 vertices, right? And then we have some relationship defined, where those edges are. And then when we visualize that overall, we get a cube. But when thinking about this mathematically, just think about each of the points as sort of moving, okay? All right, so recall that the diagonal of the scale matrix represents the x, y, and the z. Okay, so recall, or maybe this is our first time looking at it, but here's the diagonal of the matrix. And you can see s of x, s of y, s of z. That's the scale here. Okay, so that's how much I'm scaling the x, y, or z points. So I'm doing multiplication of the x points, the y points, and the z points. Okay, if these are ones across, I'm not changing everything. If x is a 10 here and everything else is a 1, then I'm scaling in the x direction by 10, which is sort of what's going on here, right? Along the x-axis, I'm lengthening everything. Okay, these points here stay still because their x value is 0, right? They're at the origin here. Okay, whereas these ones are at 1, and then I guess we're going 2, 3. So I'm multiplying by 3. So this would be 3, 1, 1, 1. Okay, here's the scale matrix again, just in 2D. Again, this is how much we're multiplying the values along the diagonal. So scale matrix is nice here. Okay, here's what the multiplication looks like, right? If you do the actual matrix multiplication, good exercise, right? Where we take the rows, row 1 times, or rather the dot product of row 1 and this column 1 here. And we get this, and then row 2 and column 2 here, and then we get this here. So 0 times x is nothing, s of y times y, that's what gives us this equation. And this is a 2 by 2 times a 1 by 2 matrix, so we get a 2 by 1 vector here, just with an x and a y value. Okay. Okay, so let me, so again, maybe that's a little bit too fast for you, but just a little bit of a refresh here. And I would say, actually, if that was a little bit too fast for you, go ahead and just write this out just as a good review last time of taking the dot product of the row times the column here. Okay, so this is a good chance to pause the video and just say, hey, I got this answer and why this sort of makes sense, okay, in the scale matrix. And then, we can build some more intuition here with a little visual here. I like to use clocks because, you can pay attention to the numbers on the face of the clock to see how things change. But this would be an example of applying a scale matrix of 0.5 on the diagonal. So we're effectively halving everything. So this y point where it gets halved. This x point, or this point here, it gets halved. And then, its x has to be halved too. So it ends somewhere around here and so on, right? So you get this clock here. Okay, so you made this object a quarter of the size. Now you don't always have to scale things uniformly, right? The diagonals can be different. So this one was 0.5, 0.5. This one's 0.5 by 1.5, right? So this effectively is like squishing the clock because the x coordinate's getting smaller and then lengthening it out on the y coordinate here, okay? All right, let's look at another transformation here. This one's called a shear transformation. Okay. Now a shear is an operation that pushes an object sideways, so it sort of skews its direction. Okay, so note the shear in the x direction is going to move points to the right in proportion to the y coordinate. Okay, so it's not scaling it here, but in our last coordinate here, this is, again, in our second column, this is the x position here. So we are, again, moving proportionally to the y. And this one, if you haven't seen it, and it works in 3D as well, it's easier to visualize. So here is the x shear direction. So I'm essentially just taking my points here in the y coordinates and I'm moving them over in the x direction. Once we learn about this last column, this will also make a little bit more sense here, but we're just taking this point, moving over here, and then this point, moving it over 1 unit here, and just stretching it in that way here. Okay. Now, y shear is very similar here. We are taking our points, okay, that are on the corner here, grabbing them, and then just sort of moving them up 1 unit here, and this is the y shear. So it's almost an optical illusion as well when you look at these. So sometimes it is helpful to draw some lines across these just to be like, yeah, that was exactly 1 unit, because it can be a little bit hard to see the actual scale here. But this is just a nice way to illustrate that, yes, things are proportional here. This is grabbing this point, moving it up, grabbing this point and moving it up. Now, why didn't we move up these points here? Because, they're on the, well, their x value is 0, so when we're trying to move these points up, they don't move anywhere, okay? So this is the y shear, okay? All right, so here's just a real world example of it. And again, you don't have to memorize these matrices, but I want to show you that they exist because they occasionally are useful. But here's just a real world example if you wanted to sort of do some sort of facial animation and make this character smile, right? You might use that for the lips here to sort of get a more natural movement here, right? You're sort of doing the shear here, sort of mirrored across the face so that the lips curl and you smile. All right, so let's get into some of the other transformations. These are the rotation transformations, okay? And rotations are actually quite important to get right so that things look natural, right? So if I have a mug here and I'm rotating it, okay, about its y-axis, why the y-axis? Well, do your right-handed rule. Remember, your thumb is the x, your pointer is the y-axis, your middle finger is the z-axis. So if I'm rotating about the y-axis, that's the thing that's pointed up. So I'm rotating around this way. Okay. But the origin is fixed when I'm doing this rotation. Preserves distance means this object here isn't stretching in any way, right? It's not scaling. And then the orientation is also fixed, right? So if you look at this N here for northeastern, when I'm moving it, right, the N isn't like flipping or doing anything weird. Okay, so these are the sort of harder properties that are preserved when we rotate. Okay, again, not things that you have to memorize, but should maybe have some intuition about for how this is working. Okay, so one thing to keep in mind is to always think about which axis you're rotating about. So again, let me give you this pop quiz, something to think about, and go ahead and pause the video and take a moment to think about this. And if you took a moment to think about this, well, I gave you a little bit of a hint. We are rotating about the y-axis, okay? So again, you got to see it spinning. Usually, again, in our coordinate system for this course, y is up. Some of you folks who have done maybe CAD modeling or maybe some 3D modeling, z is sometimes up. So if you said that as a correct answer, that's fine, but we should have been using this coordinate system here, I suppose. All right. So very good. Hopefully you got that. If you need a little bit of recharge to, refresh on your right hand rule, go ahead and take a few moments to do that as we talk about our rotations. All right. So just to give, some more intuition and sort of thinking about matrices, I mean, let's just start with 2D here again, just kind of starting slow here and figuring out what's going on here. So, let's say I have a vector A, that's this line right here, and I want to rotate it by some angle here, this angle here, okay? So, this angle produces a new vector when I do the rotation here, right? So it's already up here, okay? So, but I want to rotate it some more. Okay, so on a 2D axis, that means we're essentially sort of swinging. Think about it like the face of a clock, this vector here. And then that's what gives us a new vector here. Okay, so let me get out of the way here. But this is effectively this angle that we were at, whatever our original angle is, plus this new angle here, this phi here. Okay. So this rotation, or how to sort of understand rotations, can be derived from polar coordinates. Okay, so maybe you did these a while ago, but again, so we sort of had some angle here. This looks to be about 45 degrees to me. It's right here, so somewhere between here, and then we want to rotate it by some other angle here. Okay. So some things that we need to know about are the magnitude of the vector, right? That gives us its length here. And in this case, if we just have a vector from the origin, that's also sort of its length here, which is useful. Okay. And then any vector that we rotate, well, that vector better still have the same magnitude, again, like the clock face, right? When it's, these old-fashioned clocks, the second, minute, and hour hand shouldn't be lengthening in any way, right? When we do the rotation, that was one of our properties. And then here's sort of our conversion, though, to our coordinate system, polar coordinate system right here. So if we have some vector that's pointing here and we want to move that point or sort of rotate it, well, we got to get things in polar coordinates. So the x and the y, okay, that we're going to be at, is related to the radius here, which is the length of our vector, and then the cosine of an angle. Okay, and we have a new angle here because we had this angle A here and we added something to it. So we'll have to resolve cosine of, angle plus a new thing to figure out where we are. Okay, so it looks something like this. Here was our point here. Here's our conversion on the polar coordinate system, right, to do the rotation. Our old angle plus the new angle that we want to rotate, and then we get this here, okay? Okay, now what is this thing here? Well, this is one of your trigonomic identities for adding two angles together. Again, not something that you have to memorize for this course. For all intensive purposes, you just need to know about these matrices and when to use them, but I want to show you the derivation so you can have a little bit of appreciation and connect some of the math that you have done, and just to understand once you get down to transforming things, which tools to use. But again, anyways, here's the identities here. So we're adding two angles together, and probably something you saw a long time ago, maybe you had to memorize, but voila, here in computer graphics, you actually get to apply it. So intuitively, though, I just sort of notice four sort of terms here. There's one here, another term here, another term here, another term here. And that actually kind of starts to look like some of these rotations that we have here. I mean, let's look at our x rotation here, where I have a cosine here. I have a negative sign here, but I have a minus r sign here. Then I have a sine symbol here, and then I have a positive cosine here, okay? Now, why did I choose the x rotation? Well, if I do my right-hand rule, and, depending on how I'm pointing this, I guess, let's see. For the camera here, again, Z is towards me, and I'm rotating about the x-axis, so where my thumb is, or I guess it could be the Z. It doesn't really matter, but it's just showing the alignment of cosine, sine, and sine and cosine here. Okay. So just looking at this for a moment, and hopefully it took a moment here to also take a moment to just see what's going on here. Right, this equation can be reduced to what's shown on the right side here, right? So I have x prime equals r. So here's the addition. Here is this trigonomic equation here, and then somehow I get it to x prime equals x cosine theta y minus theta. Okay, now how did I get there? Well, consider that r cosine of phi here, okay, that's this symbol here, equals x, and r sine of phi equals y here, okay? Where does that come from? Well, recall x prime, that's a new angle that we're doing, right? This just comes from r cosine of phi here. Again, let me go back a little bit here. Right, these formulas here. R cosine of something just gets x of that angle. R sine of something gets y of that angle. Okay, so that's all that's coming in here. That's where this substitution gets. And then again, this is another way to observe cosine minus sine. Here's cosine minus sine. Here's sine plus some cosine value, sine plus, and then there's some cosine here. So I can kind of divide these up here. Again, just trying to build your intuition here a little bit. Okay, so here's the sort of 4 individual terms here, okay, in our matrix. Okay, all right, so the ordering, cosine, sine, etc. Spatially, it stays the same. Cosine minus sine, sine, cosine, cosine, sine, minus sine, cosine, cosine, minus sine, sine, cosine, okay? Why is there a 1 in some of these positions, though? Okay, and I'll give you a moment to think about this for a moment. All right, and hopefully you paused the video and took a moment to think about this, but well, ask yourself what this column is or where terms sort of show up. You can think about this in your scaling matrix, right? Here's the x term, here's the y, here's the z. So during my x rotation, I have a 1 in this sort of x position. In my z rotation, I have a 1 where the z is. In my y rotation, I have a 1 where the y is, okay? Y rotation, so I get a 1 here, because those points shouldn't be changing, right? When I'm rotating about the y-axis on my mug here, it's not hopping up and down, right? It should preserve its location. Everything else is changing on some plane, but I'm not hopping up and down. So the y-coordinate here in the middle stays the same here, okay? All right. So that's the axis that you're rotating about, and we don't want those points changing on that axis if you're rotating about that axis. All right, so it's a little bit subtle as well. As I mentioned here, our rotation matrices have this property, and I sort of gave it a name at the start of talking about rotations, but this means that they're orthonormal, meaning that the points don't get stretched or anything. Okay, everything stays proportional as it moves around. Again, this mug that I have doesn't get stretched or scaled in any way. Okay, so just something nice to know, some properties here. Okay, so here's just an example, doing a rotation here. Again, you could pick one of these points or draw a vector out from our original one to one of these points here. And when we rotate it, right, we're applying that rotation to this point here and rotating it, okay, by, say, 45 degrees, okay? All right, and intuitively, in these examples, I'm talking about 45 degrees, 90 degrees, because those are things you understand. But just a heads up, when we're programming, typically we're using radians. Why? Well, you can click this link if you want to explore a little bit further. The answer tends to be it's a little bit simpler to work with computationally. Also, if you're doing things like computing, like arc length and some of these things, they just work a little bit better in radians as well. All right, so for 3D matrices, some of the things that we're actually going to do later on are building things like solar systems and thinking about some of these rotations. Here it is in 2D, but and the relationship between these objects and how they rotate. So we'll really get a chance to sort of exercise some of those here. Now, something that comes up with rotations that could be a problem in 3 dimensions, and I don't know if you've ever had one of these gimbal tools, this is what this is called, or illustrating here, is that if you rotate on all 3 axes at once, whenever the 3 axes align, you actually lose 1 degree of freedom. Okay, now again, this is sort of a weird property that occurs here, and perhaps it's sort of explained very nicely in one of these videos here, so you can see the actual problem. But this is actually something where we need to use a different coordinate system to figure out this problem. Again, so if you have 3 dimensions and when all these gimbals, so the blue, which represents an axis, the green, which represents an axis, and the pink represents an axis. So all these inner circles, right, are the different axes. Um, you lose one. So in order to fix this problem, you essentially use something called a quaternion, which is a different style of math, which still has this problem, but it essentially just adds an extra axes. And then it's actually quite clever. There's a nice story about it in a place in Ireland you can visit if you want to see the actual where this was invented. But you have 4 dimensions, and then when you lose a dimension, you still have 3 dimensions, which is good enough for us, right? Because we just need an X, a Y, and a Z. So just a little bit of an aside here that you can explore. Or if you've done a little bit of game development already, you might want to say, hey, why is Unity 3D or this tool always using quaternions? All right, now there's another nice aside here by Justin Solomon, a professor out of MIT, just on deriving rotation matrices if you want a little bit more intuition beyond what I've provided. Hopefully those examples were useful. Some other things I'll say is sometimes it's convenient to think about things in terms of the pitch, yaw, and roll. And these are sort of when think about like an airplane, for instance, and how it's rotating. Again, depends what type of problem that you're trying to solve. But again, the pitch of the plane, right? You're going for a takeoff and it's sort of rising. But while the airplane's sort of mid-flight, turning left or right, that's the yaw. And then hopefully you're never on an airplane where you do a barrel roll, but that would be essentially rotating about the z-axis. Okay, something like this. Anyway, so here's an airplane from a game, Star Fox, doing a barrel roll. Hopefully you never do that in an airplane. All right, let's talk about a few other transformations. This one that's coming up, reflection. So maybe we'd like to reflect a vector. Okay, and this can sort of create a cheap mirror effect. So if I want to reflect about the y, I'm saying, hey, all of my x points, you're going on the opposite side. If I want to reflect about the x-axis, I say, hey, all of my points on the y, you go the other direction. Okay, we're negating a vector which sends it the other direction. Okay, but along a particular axis. Okay, and this is a little bit more clear way to see it, reflecting about the y-axis. So we say, hey, here's our y-axis. Think about the y-axis sort of as a door hinge, and then you're just flipping the other way. Or I guess in this example, we're starting here and then we're just flipping to the other side, our points. So you can see the face of the clock is now backwards because we've grabbed this corner and wrapped it around to the other side. All right, and here's, of course, reflecting about the x-axis, same idea. We're saying, hey, the x-axis is here, and drop all the points down. All right, now another thing for you to think about here. Here's just kind of a cool scene I found, and I was wondering what sorts of transformations do you think are being used to create this effect here? Because we've got this sort of water effect and so on. So go ahead and think about it for a few moments, and then we'll, well, you'll see what you came up with, and I'll share my answer. All right, so hopefully you had some time to think about this, and there's actually a couple different ways you could sort of get this transformation. But the reflection that we just talked about, for instance, of sort of mirroring this scene here, and then maybe using a shear, which we talked about a little bit ago, to get the wavy effect, along a sort of sine wave. So that would be at least 2 transformations that you probably have to combine here. Now maybe you could also, for the water, at least this transformation, what you're essentially doing is taking a camera from the water's perspective and sort of looking up and saying, hey, what can I see? And that's where you're reflecting back down. But maybe you could also argue with me that there could be some sort of like rotation here, depending on how it's moving. It looks a little bit more wavy, like a shear operation. But anyways, one thing I just want to, again, sink in or get an early idea is we have something called a fragment shader, which we'll talk about when we get to OpenGL for doing these sort of effects, but at a pixel level. So truly moving pixels around. Okay, so just something kind of fun to take a look at here. All right. So our next topic, as I disappear, is going to be matrix composition, and that is, again, the same thing as matrix multiplication, but I really want you to think about this as matrix composition, applying one transformation after the other, and that's how you get your actual final matrix. Okay. So the real power of matrix transformations, again, is this ability to transform them one after the other, because we're essentially just doing matrix multiplies here. Okay. So again, as an example, we could apply a scale transform to a vector v1, and then we could rotate it. We could scale it again and rotate it again and transform it, and etc., etc. And that gives us a final product. Okay. Now a key thing, and let me get my camera working again so I can, tell you this is important. I'll give you 1 second to come back. But we read these transformations from right to left. So this guy right here, and I'll move out of the way, we are multiplying this vector, we are scaling it first, and then rotating it. Okay, so exactly as I have written it up here. Okay, the order that's occurring matters. Okay, we work right to left. Okay, right, so here's the same thing, right? So both of these are the same. I can move the parentheses, I can scale the vector and then rotate it, or have the vector and scale and rotate it, but I'm always going right to left, which again, if you're used to reading left to right, is weird, but that's just how the transformations get composed. Okay. All right, so if I'm composing matrices, does the order of operations matter? Well, let me give you 2 seconds to think about this. The answer, well, there's actually a better way to think about this. I mean, I just gave you the answer, but go ahead and do this exercise where you stand up and start at a location, walk, turn left and walk 10 steps, and then kind of remember where you're at. And then go back to your same starting location, the same orientation, and then do the same experiment where this time you just walk 10 steps forward and then turn left. You're going to be in 2 different spots, hopefully, if you do this experiment right? So follow these directions here. And then that's the answer, right? Order matters. All right, so always remember that with matrix multiplications. Think of it like concatenation. It's really composing transformations together. So here's just an example here of doing a scale first versus a rotate first, and you end with 2 clocks that look different. Okay, so the transformation order matters. And here it is, just illustrating again, the first transformations on the right, and then we go left, and then left again if we have more transformations. Okay, so here's just some more examples showing, rotating and then translating, right? So if we translate out first and then rotate, that gives us, again, something much different than just rotating and then, walking forward. After we've done this transformation, we've effectively, all these vectors are at new points. So when we rotate them, we're moving on a larger axis here. Okay. All right. Now you'll notice that we haven't yet talked about translation yet. All right. But in order to talk about translation again, I want to talk about a sort of category of transformations, affine transformations. And this idea that, there's actually no way to really move an object to translate it. Even when we're sort of rotating things or, moving vectors around here, this doesn't really work with a 2x2 matrix, okay? Because we need to do some sort of bookkeeping to move the points here, okay? So just kind of follow with me, and if you want to just take it out as it is, that's fine. But again, I want to give you some intuition here, right? Because you're going to have to know this as a graphics engineer for how things sort of work here. So the trick is, or what we end up doing in graphics, so this is in a 2D world, so we actually add another row and a column, so we make this a 3x3 matrix. And this last column here, you'll see X subscript T for translate, and YT for translate as well, is what sort of keeps track of the translation. Really what it's doing is sort of setting up a way for us to move you'll notice the X and the Y points here as part of our matrix operations. And the last one here, well, I'll talk about that in a moment, but that sort of has to do with our perspective or distance away from the camera. So this is always could be 1 anytime we're doing some sort of transformation here. Okay. So why is this point 1? Well, again, my graphics professor just told me it's always 1, but again, I want to try to give you a little bit more intuition here. So if we're, again, doing some sort of movement, or this matrix represents some sort of position, we have a 1 here. If it's 0, then we're multiplying through or representing a vector of displacement. Okay, so it has some sort of meaning here, I guess. And let me actually skip this slide. I'll hop on. So here's why the sort of W equals 1 here. And sort of a nice analogy here. And again, we might not have this intuition right now, but that's okay. But basically when we say when W equals 1, we're not scaling. So again, maybe the easier way to think about this is just how much do we want to scale our scene by? Well, if it's 1, we're not making any change. Okay. So again, if you think about this like a movie projector or something, we're moving away, or rather closer because we're scaling by 3 here. Okay. Okay. So here's just an example of transforming a 3x3 matrix, some 2D shape here. So we have an X and a Y, and then we just have 1 in our last position in our vector, and then actually do the transformation here. Okay. Okay, so moving on from that, maybe that'll give us some intuition about why the 4th column here, because we need to store an X, Y, and a Z for our translation here in our matrices. So how much are we moving our point? And then the last one is sort of preserving perspective. Okay. All right, so at this point, if you've watched this far, make sure you give yourself a 5-minute break as you need. And if you've taken a break, recharged a little bit, let's go ahead and finish off the second half here. And we're going to talk about viewing. So getting into this idea of view space. Okay, so we have a special matrix for this. We call it the projection matrix, which holds, well, really it's just a matrix that holds values that are going to tell us how do we, after we've moved all of our points in the right space, then project them so they look like we have projection. Okay, so a little bit more intuition on projection here. Again, our goal is to render a 3D scene here. So when we have a projection matrix, and this is sort of a nice example here of taking a 2D point and figuring out where these points land here. Okay, so projection basically means we are reducing a dimension. Okay, so when we project a 3D point onto a 2D screen, we need a projection matrix for that. Okay, we learned about projection operations with a vector where we essentially said, hey, where does this, if I projected one vector onto the other, where does it land? Sort of on that vector. And you can imagine that other vector is sort of a number line. That's the sort of operation. So you can think projection as reducing a dimension. All right, so again, it's always useful to think about when we've been doing these transformations as sort of moving an object or a point around. But we can actually think about this in 2 different ways. We can think about, hey, moving a point around, like here's my mug and I moved it to the right. Or I could think about it as, hey, I moved it to the right so it landed here. Or maybe I moved the entire world, which I'll try to do this. So like this. And right, it's still over my right shoulder. Right, either way, whether I move it to the right here or if I move myself. So I can either move the entire world or move all of the points and keep the world around me. And what I'm getting at here is this is the camera, right? So imagine it, allow me to provide another analogy here. Let's say a famous director, I don't know, Steven Spielberg or somebody, says, hey, we need you for a movie, fly to California and be on the set at 8 a.m. For the movie. Or what we could do is we could say, hey, Steven Spielberg, you come to me and build the set in my house and I'll be here at 8 a.m. right? It's the same effect, right? The movie set's still going to be there. Whether you're moving yourself there or moving the entire set to you. Okay. So here's just sort of two examples of that, and that's how we can sort of think about a camera or a virtual camera in computer graphics. How we want to move this world. Just move all the points by this new matrix, so doing another multiplication, or apply the camera to all the other points. Okay. So this is the example I did with the mug here, just showing that, hey, if I've got this coordinate system and I shift it over 1 unit here, that works. Or I can move the entire coordinate system here. Okay, actually, this is probably the easiest view to see it. I can either move the point here to the left or move the coordinate system to the right, okay, by 1. And let me actually move away here. All right, so with our math knowledge that we have, we can figure out how to solve some of these problems of viewing a 3D world on a 2D surface. I'll provide you sort of the projection matrix to do that, but again, that's just to sort of reduce dimensions. So there are a few things we need to keep in mind though when we're viewing the world, like the camera position, the orientation, the field of view, what our resolution is going to be, all these sort of properties of a camera here, okay? Because the camera or this viewing transformation, that's really our eye, whether you want to think about it like a human eye or whatever, but this is a way to think about it. Okay. And the eye does work, essentially like a pinhole camera. So let's go ahead and take a look at this image here. So again, just taking a moment to think about this. Here would be, rather, this is probably an easier screen to see here. If you've ever done a sort of pinhole camera where you're sort of looking through, I guess one way or the other, if we want to think about this as the screen here, and actually seeing the shape, it does get inverted when light comes in and it's sort of projected in the opposite direction. So on occasion in your graphic scenes, since we're simulating a pinhole camera, and that's what we're doing with our projection matrix, your object might be flipped upside down. It is appropriate or fine to just flip the coordinates, right? So reflect about the x-axis if you want to think about it that way, or just if the y point is at this position, negate it so it's at the lower position. So anyway, that's just an aside here. Okay. Some other asides, just graphics things, how fast do we see in our cameras, or maybe you've done some camera work and think about some metrics. Frames per second is our metric. How many frames can we draw in a second? That's how many times can we fill our frame buffer. 24 is typical for a movie historically. Sometimes you might go to a new film today and it'll be higher frames per second, but video games, 30 to 60 frames per second, usually closer to that 60 frames these days. If you're on a VR system, you're probably 90 frames per second or 120, so you don't get motion sick. Most of your monitors too are probably like 60 to 80 frames per second, or 60 to 80 hertz is how they measure the frequency of updates. So that's just something to keep in mind there. All right, so the 3 main transformations here. Again, to deal with the camera, right, we have our sort of eye space or our view space. That's our camera. The projection transformation, which also handles sort of clip space, and make sure that our points are within the range -1 to 1, and then we just ignore everything else. And then the viewport transformation, which basically puts things into pixel coordinates. Okay, so something that we're more familiar with. All right, so let's just go ahead and visualize these 3 things together. Again, not something you have to always remember. I can get my camera back on so you can see me. Occasionally it will go out if it's getting tired. But a very common interview question I have, and I'm actually going to put this in the notes just so you know. Note, this is a common interview question to describe this process because it tells if you understand the actual sort of pipeline or the journey of a pixel and transformations and these kind of things. But right, we go from object space or our local coordinates transform. So we apply a rotation, a scale, whatever that we want here, and that puts things into world space. Okay, so notice our R is moving around here. Then we apply our camera transformation, which says, hey, how do we want to view the world? So I can pretend you're, Steven Spielberg or whoever, viewing the actual scene through the lens of a camera. And then we do a projection. So again, this is Steven Spielberg looking through a camera, and then he decides, hey, I'm going to put this camera lens on that views it in a certain way, maybe a wide, shot or whatever. And then we go through these things that I mentioned on the previous slide here, like viewport transformation, which says, okay, here's my coordinate system. Now I just want to view things, in this, take things from this normalized range of just 0.0 to 1.0 and move them into screen space. So 0, so a 1280 by 800 coordinates, right? Your screen resolution. Okay, that's what the viewport's doing. How am I viewing the viewport? Okay, now there are two main projection types. The one that we've been, I keep mentioning, perspective. This is how we view things in the real world, or roughly some sort of linear perspective. That means things that are further away appear smaller. And then there's also a oblique or orthographic projection, which regardless, it doesn't matter how far away an object is, it appears the same distance. Now, why would we want to use this one? I'll show some examples. Let me start with perspective. Again, this just sort of simulates the real world, right? You can do this experiment, look outside your window. Things that are further away should appear smaller for humans. Different animals might have different perspectives, but this is how it works for us. And again, notice everything's sort of converging towards the center here. And here's sort of a classic orthographic example where I said, well, regardless of how far something is, the distance is preserved. And this tends to be more important for architecture, right? If you're planning the layout of a building and you want to see how things fit together, or make sure that all the hallways are spread a certain distance, regardless of where you are, the viewer, you might use this sort of rendering. Okay, so if you've done some CAD or any drafting sort of software, this is what you'll end with. All right, now some things to think about, and I know there's 3 pictures here. And I'm going to focus back on perspective view here. So here, this top left image, here's you at the bottom here. And you're looking up, so this is sort of a side view here, looking out into the scene. The projection plane's your actual monitor. Okay, that's over here. So things that fall within this projection plane, or this sort of trapezoid here, I guess, are what we can view. So anything that falls in here. Now this equation here that's related to this is saying, well, the distance of something, that's this sort of the y prime and the minus d here, it's basically just saying, hey, the things that are farther away, actually it's probably easier to see here, things that are farther away we divide by distance. Okay, and depending on how we're projecting this, it might be minus z or positive z, but we want to shrink things, okay, based off of their change in distance. Okay, y prime here, so where I'm projecting it on here, on this actual screen plane, is related to, well, I've just taken this d and multiplied it by both sides, the distance times where it is in the y, divided by z, okay? Now this image on the right here, this is also sort of related, but this is just a 3D view of this. This is a side view, right? Z is coming out, Y is up, X we can't really see, it's coming out here, but here's just the 3D view. The sort of filled in color here, this sort of purplish or bluish tint here, whatever this is the viewing volume of the stuff we can see. This thing that I'm tracing around now, that's the actual screen or the monitor that we're projecting onto. And then these are all the viewing volumes, objects that go out and they'll get projected somewhere here. All right, so here's probably a cleaner way to see this. Okay, so for our perspective view, here's you. E here is the I. Let me actually label some of these things. Sorry, and I like to do this live sometimes because it's helpful if I'm talking as I do it. And you can see me build the slides here, but slides with figures. So E equals your I, just so that you, this is where you are, okay? U, V, and W are the view space coordinates, okay? You can think about them like X, Y, Z, but again, we have a different labeling for our different view spaces, different spaces that we work in. Okay, we've talked about different spaces like world space, local space, etc. But just to keep that clear here. Okay, D is the distance, again, away that something is. All right, now, if it's helpful, again, some pictures on just the orthographic or oblique perspective. I think this is somewhat intuitive, but again, it doesn't matter how far away objects are, right? You don't see any distance D here. Our camera is right on the projection plane, so regardless of how far away something is. Here, I'll go ahead and label that as well. Note, you don't see distance or a label D here because we don't consider distance anywhere in this projection. Okay. If it's visible, it's visible. All right. Now this, the name of this thing, this sort of pyramid here that I've been highlighting, and here's again the projection plane, and the closest point that we can see, that's called the near plane. The far plane is as far out as our eyes can see, but this is called a view frustum. Okay, and that's the sort of projection or the things that we can see in our camera. Okay. All right, so it looks something like this. And this, again, I'm highlighting here is blue, here's the orange line. So I could kind of line up, here's the blue, here's the orange line. Anything that falls in this volume is what is drawn, okay? All right, so again, here's our eye here and the system, or coordinate system here. E is our eye in the sort of position here, which is at the center here. G is the gaze direction, that's where we're looking. T is the up vector, that's where up is in the world. And you can literally think about this, I know it's a little bit disorienting, as this sort of, if you put on a virtual reality headset for where you're looking, and you could imagine sort of this coordinate system there. Again, the T vector here, which is the up vector, whereas up point, and I'll sort of recreate this, right? You could do this as an example. So just take some object like a pen, stick it on the top of your head, and then when you're looking up, that's changing directions. That's where up is in the world, okay? And again, we've talked about there's various reasons why you want to keep track of this up vector for when you're, say, rotating your head left or right, so that you can actually rotate about in axis, okay? Which would be the up vector that you're rotating about. All right, so where our eyes can see is called the field of view, okay? Let me sort of advance one step forward. And we sort of calculate this, well, this is what our lab's actually going to be about, but right, when we have a triangle like this, if we make it into a right triangle, and this is where I'm starting from and I'm looking out, well, this opposite edge here and the adjacent one, if I know the angle, that can compute my field of view, okay? That's what our lab's going to be about. I'll talk about this in a few moments. All right, so this is, a lot, or sort of crash course to some of our, again, transformations, matrices, hopefully getting some intuition about how they work. But sometimes it's nice to hear others' perspective here. So, their perspective matrix. So some examples from an online Unity course, or Udemy course, that I'd like you to take a moment to look at. This one explains a little bit the distance and how things get foreshortened, right? So these trees are actually going to appear the same size. I'd like you to take a moment to pause the video and just watch this 1 minute video in length here. I think that'll help make things a little bit more concrete. Once you've done that, then there's another 3-minute video on look at, or your eye, sort of how to model an eye and a function to look at things. I'll get out of the way so you can see the equation if you want, but it's explained in the video. So do take a moment to do that. And then the translation matrix. There's actually videos for all of these if you'd like to watch, but translation, because that's the mysterious one, and the reason why we have to add this extra row and column to use 4x4 matrices in 3Ds is a good one as well. Okay, rotation matrices if you want to see as well. So with that said, that's it for the actual lecture portion, but I do want to take a moment or two to dive into the lab here and just show you what you're going to be working on. Let's go ahead and open up the monorepo. And you're going to be working on a perspective star field. Now, admittedly, this is probably the quickest lab that you're going to do, but you're going to be building this star field here, okay? So let me actually dive into the repos here. I'll give you one moment. So what you're going to have here is, if I dive into lab 4, the perspective star field, as always, you run the build. And, well, let me go ahead and show you what you start with. You're going to start with something that looks like this here on the right, where some stars are just popping up, essentially. But this is a little bit weird. This doesn't look like the left effect, which is pretty cool. And the reason you don't get that effect here is because we're not considering the actual distance here, okay? So let me go ahead and remove this lab here, because I'll push it out to you in a moment. So what you're going to figure out, and it's admittedly a short lab, is how to create that star field effect. And there could be some variations in what they look like depending on what sort of field of view you use, but you're going to have to consider in your perspective, and again, there's not too many lines to actually change, how that is done here. Now there's a helpful supplemental slides that I'm providing here, so you can go ahead and click through those and sort of understand this problem of what we're actually doing, how we're creating perspective. And I alluded to this idea of, well, when you're sort of looking across a scene, if you sort of, your view frustum, chop that triangle in half, then you have a right angle. And then, well, we can work with triangles that have a right angle quite easily, right? We have the tangent, which gives us the sort of opposite side, and then we have the adjacent side, which is measuring the distance, and then somehow we can use that to create perspective here. Okay, so I'm going to let you flip through this, but I just want to make it explicit that this is sort of a useful handout for you. Okay, so I'll have that link there for your lab. And I think with that said, I'm going to go ahead and end the video there. If you have questions, go ahead and post as needed, and visit office hours, and we'll get you taken care of. All right, bye for now, folks.